Assalamu alaikum. Bismillahir Rahmanir Rahim. I welcome you to the 34th lecture for the series of lectures on advanced computer architecture. Today we are going to start with new concept, that is the use of multiprocessing and thread level parallelism. After a brief review of what we have discussed so far, we will be talking about what is parallel processing and what are different architectures available for parallel processing employing symmetric shared memory and distributed shared memory. Then we will also talk about the performance of parallel architectures. As you know that so far our focus has been to study the performance of a single instruction stream computer. In this respect, we discussed different methodologies to enhance the performance of such machines. During our earlier discussions, we studied how the instruction level parallelism is exploited amongst the instructions of a single instruction stream architecture, and the control, data, and memory dependencies are resolved. In our discussion regarding single instruction stream computer, we discussed different methodologies to realize the systems, and these systems are the pipelining in the data path. Then we also discussed the superscalar architecture, very long instruction word architecture, and methodologies for out of order execution. All these techniques were discussed to enhance the overall performance of a single instruction stream computer. Then we extended our discussion to the memory hierarchy, wherein we discussed how we can organize different types of memories such that the fastest bit rate is provided at the cheapest cost of the memory. However, what we can note that we can improve the performance of a computer further by using multiple instruction streams instead of using a single instruction stream and the pipeline architectures. Here, in this particular technique, we use the methods of multithreading, which deals with the execution of number of instruction streams running onto a single PC. Or we can use the method of multiprocessing, which uses the concept of number of streams running on multiple CPUs, where each CPU can itself be multi-threaded. In order to discuss this particular technique and in order to see the impact of the parallel computer performance, we can make use of the Amdahl's law while evaluating the performance enhancement due to parallel processing. Now, we can note that, in fact, there are two important challenges which are to be taken into consideration while talking about the performance of parallel architectures. These challenges are, number one, the limited parallelism available in a program, and number two, the high cost of communication. Now, these limitations make it difficult to achieve good speed up in any parallel processor. We can understand this particular problem with the help of an example where, if we assume that a portion of a program is sequential and it is this part of the program which in fact limits the speed up. We can understand this with the help of this example where, if we have to compute the fraction of original computations that can be sequential to achieve speed up of 80 with a parallel processing system having 100 processors. In order to study this impact, let us consider the expression which we discussed earlier in our initial third or fourth lecture, the expression for speed up, which is that 1 over fraction enhanced divided by the speed up enhanced. This ratio is added with 1 minus the fraction enhanced. This you can see over here that a speed up therefore can be calculated for the given example, and it results in a value which shows that, as you can see from here, that the fraction parallel is equal to 0.9975. That is, in order to achieve the speed up of 80 with 100 processors, only 0.25% sequential operations are allowed. The second major challenge in the parallel processing is the communication cost. The communication cost basically involves the latency of remote access. Once again, in order to discuss the impact of the latency and communication cost onto the performance of a parallel computing system, let us consider another example. Here, in this example, we are considering an application running on 32 processors multiprocessor with 40 nanosecond time to handle the remote memory reference. We also assume that the instructions per cycle for all memory reference hit is equal to 2, and processor clock rate is equal to 1 gigahertz. Then let us see how we can find out how much fast is the processor when there is no communication versus 0.2% of the instructions involve remote access. For this example, we can calculate the clock cycles per instructions as it is equal to the sum of the base clock cycles per instruction and the product for remote access request rate and the remote access cost. Now, for this example, you can see that by substituting the values from given example into this expression for clock cycles per instruction, we find that the clock cycles per instruction with remote reference is equal to 0.5 plus 0.8, which results in a value equal to 1.3, whereas the clock cycles per instruction without remote reference is equal to 0.5, which shows that the multiprocessor with all local references is approximately 2.6 times faster than the multiprocessing without any remote reference. Now, considering these limitations, let us explore how improvement in computer performance can be accomplished by using parallel processing architecture. Here, let me first of all define what do we mean by parallel architecture. Parallel architecture is a collection of processing elements that cooperate and communicate to solve larger problems at a very fast speed. The parallel computers extend the traditional computer architecture with a communication architecture to achieve synchronization between threads and consistency of data in caches. Basically, it was in 1966 when Flynn proposed 4 simple categories of computer, and we can say that these categories are still valid even today. The categorization proposed by Flynn forms the basis to implement the programming as well as communication models for parallel computing. Flynn looked at the parallelism in instructions and in the data streams called for by the instructions and proposed the following 4 categories. Number 1, single instruction, single data, that is SISD. This category is indeed the uniprocessor category. That is, there is a single instruction and single data stream available which can be executed or processed onto a uniprocessor. The second category is referred to as the single instruction, multiple data. It is abbreviated as SIMD. Here, the same instruction is executed by multiple processors using different data streams, and each processor has its own data memory. That is, the multiple memories exist in the architecture. However, there is a single instruction memory and a single data memory. The examples of Such computers are ELIAC-4 and CM2, where these systems offer simple programming model, very low overhead, lot of flexibility, and the whole system is developed by using custom integrated circuits. The third category proposed by Flynn is multiple instructions, single data, that is MISD. Here, multiple processors or consecutive functional units are working on a single data stream. However, at present, no commercial multiprocessor using MISD technique is available even today. The fourth category is referred to as the multiple instructions, multiple data, or MIMD. Here, each processor fetches its own instructions and operates on its own data. So there are multiple processors and multiple instructions, and each processor can fetch its own data and its own instruction, and it can process it. The typical examples of MIMD machines are the Sun Enterprises 5000, Cray T3D, and SGI's Origin. The characteristics of these machines are that they offer flexibility. It can function as a single user multiprocessor or a multi-programmed multiprocessor running many programs simultaneously. Furthermore, an MIMD machine can be made by using off-the-shelf microprocessors. The MIMD machines have multiple processors, and they can be used either each processor executing different processes in multi-programming environment, or multiple processors executing a single program, sharing the code and most of their address spaces. In the latter case, where multiple processes share the code and the data, such processors are referred to as the threads. The threads may be either large-scale independent processes, such as independent programs running in multi-programmed fashion, or a thread may be a parallel iteration of a loop having thousands of instructions automatically generated by a compiler. Such a parallelism in the threads is referred to as the thread-level parallelism, and we will be taking into consideration the effect of thread-level parallelism on the overall performance of multiprocessor architecture. Now, before we go into further details of multiprocessor architectures in general, let us discuss the classifications of the multiple instructions, multiple data architecture, which is most commonly used as the multiprocessor architecture. The classification can be made based on the memory organization and its interconnection strategy. Based on this, the MIMD machines can be classified as either centralized shared memory architecture or distributed or decentralized shared memory architecture. Let us first of all study the centralized shared memory architecture. The centralized shared memory design, which is shown here, it illustrates the interconnection of main memory and input-output systems to the processor cache subsystems. In small-level designs of centralized shared memory systems, where we have, say, less than a dozen of processor caches, the subsystems share the same physical centralized memory connected by a bus, while in larger designs, that is, the designs with a few dozens of processor cache subsystems, the single bus is replaced with the multiple buses or even with a switch which is used in the system. However, you can note here that the key architectural property of this centralized shared memory system is the uniform memory access, or say UMA. From UMA, we mean that the access time to all memory from all the processors is same. So this is the key property of the centralized shared memory system. Furthermore, the single main memory has a symmetric relationship to all the processors. These processors are therefore referred to as the symmetric multiprocessors or SMPs. This style of architecture is also sometimes called uniform memory access architecture, or say the UMA architecture, because it offers uniform access time to all the memory from all the processors. Now let us have a look onto the decentralized or distributed memory design style of multiprocessor architecture. This architecture, as it is shown here, it consists of a number of individual nodes containing a processor, some memory, and input-outputs. And all these are connected through an interface to an interconnection network that connects all the nodes together. The individual nodes here contain a small number of processors which may be interconnected by a small bus or a different interconnection technology. Furthermore, it is a cost-effective way to scale the memory bandwidth if most of the accesses are to the local memory in the node. Hence, we can say that the distributed memory provides more memory bandwidth and lower memory latency. Hence, this makes the design more attractive for small number of processors. However, this technique has some disadvantages. The basic disadvantage of this system is that the data communication between the processor is very, very complex, as there does not exist direct connection between the processors. So, with this much introduction to the two types of MI/MD machines, let us have a look onto the issues which are to be taken into consideration while talking about the parallel architectures. These issues are: we have to look into how large is the collection of processors. We have to note how powerful are the processing elements and how do they cooperate and communicate with each other. Furthermore, we also have to see how the data is being transmitted and what type of interconnection is to be used. Furthermore, we also have to take into consideration what are the hardware and software primitives for the programmer and how does it translates into the performance. While considering these issues, we can classify all these issues into three distinct types, that is the naming, synchronization, and latency and bandwidth. First of all, let us talk about the naming. Naming deals with how to solve large problems fast, how the data is to be named, which is to be shared, what data is to be shared and how it is to be addressed, what operations can access the data, and how processors refer to each other. For this purpose, the segmented shared address space locations are named uniformly for all processors of the parallel program, and this naming can be expressed as the processor number, comma, the address. The choice of naming indeed affects the code produced by a compiler. This is because of the reasons that for message passing via load, the compiler just remembers the address or it keeps track of the processor number and local virtual address. The second is replication of data, because in case of cache memory, the replication and consistency through load or via software is affected by naming. The global, physical, and virtual address space is also to be taken into consideration by naming, because the naming determines if the address space of each processor can be configured to contain all the shared data of the parallel program. The second issue is regarding the synchronization. We have just discussed that in parallel machines, to achieve synchronization between two processes, the processes must coordinate in respect of message passing and shared addresses. Message passing implicitly coordinates with transmission or arrival of data, whereas the shared addresses explicitly coordinate through additional operations, for example, by writing a flag or awakening a thread or generating an interrupt to a processor. The third issue is regarding the latency and bandwidth. We need high bandwidth in parallel communication. However, the bandwidth cannot be scaled, but it stays close to the requirements. Furthermore, the bandwidth must match the limits in the network, memory, and processor. It also have an impact onto the communication in these machines. Whereas the latency affects the performance, because processors may have to wait, because this means that when multiple processors are sharing, then sometimes one processor may have to wait before the required data or the required address space is available. The latency also affects ease of programming, because it requires more thought to overlap communication and computations. Now, these issues can be taken up while designing the parallel processing architecture. For this purpose, let us describe a framework for parallel architecture. A framework for parallel architecture can be defined as a two-layer representation where these layers define programming and communication models. These models present sharing of address space and message passing in parallel architecture. The shared address space model at the communication layer defines the communication via memory to handle load, store, and etc. And at the programming layer level, it defines handling of several processors operating on several data sets simultaneously, and to exchange information globally as well as simultaneously. Whereas the message passing model at these two layers behaves as follows. That is, the message passing model at the communication layer defines sending and receiving messages and library calls, whereas at the programming level, it provides a multi-programming model to conduct lots of jobs without input-output communication simultaneously. Now, with this much introduction to the framework for parallel architecture, let us discuss the shared address space architecture for decentralized or distributed memory architecture. The shared address space is also referred to as the distributed shared memory, that is DSM, where each processor can name every physical location in the machine, and each process can name all data it shares with the other processes. Furthermore, the data transfer takes place via load and store in this particular case. For shared address space architecture, data size is defined in terms of bytes, words, or cache blocks, and it uses virtual memory to map virtual to the local or to the remote physical. Processes on multi-processes are time shared, and multiple private address space offer message passing multi-computers via separate address space. Let us have a look onto the programming model for the shared address space architecture. Here you can see that the programming model defines how to share code, private stacks, some shared heaps, and some private heaps. Here, process is defined as virtual address space plus one or more thread controls. Here, note from this figure that multiple processes can overlap, but all threads share a process address space, that is, portions of address spaces of processes are shared, and writes to share address space by one thread are visible to the reads of all threads in other processes as well. Now, there exist number of architectures which are implemented using this programming model for shared address space architecture. The most popular architectures in this respect are the mainframe computers. The mini computers are symmetric multiprocesses, the dance hall architecture, and distributed memory or non-uniform multiprocessor architecture. Let us have a look onto the mainframe architecture. The mainframe architecture was in fact motivated by multiprogramming. As you can see here, it extends the crossbars for processors interfacing to the memory module and to the IOs. Initially, this architecture was limited by the processor cost. However, later on, it was limited by the cost of crossbar because the design of crossbar was too expensive. Therefore, it needed considerations. The typical example of mainframe architecture is IBM S390, which is presently known as the Z server. This design employs the crossbar architecture. The second type of architecture is the mini computer architecture or SMP architecture. This architecture was also result of the motivations for multiprogramming and multi-transaction processing. Here, all the components are on shared bus and all memory locations have equal access time. So, this architecture is referred to as symmetric multiprocessor architecture or SMP architecture. However, the bus here is the bandwidth bottleneck because here in this particular case, sharing is limited by bandwidth when we add processors and IO. Because if we go on increasing the IOs or the processors, then the bandwidth for each IO or each process will be limited. Furthermore, caching is key to the coherence problem in this case. However, I will be talking about this cache coherency problem in detail in the following lectures. The typical examples of an SMP architecture is the Intel Pentium Pro Quad, which is shown here. In this particular architecture, all the coherence and multiprocessing is joined together in processor module, and the whole of the design is highly integrated and it have low latency and bandwidth. The third architecture, referred to as the dance hall architecture, is shown here, where you can see that all the processors are on one side of the network and all the memories are on the other side of the interconnection network. This architecture offers solutions to the problems faced in the crossbar architecture and SMP bus architecture, where the interconnection and bandwidth were found to be the bottlenecks. Here, in this architecture, scalable interconnection network is used where the bandwidth is also scalable. Hence, it provides solution to the problems as we faced in the case of the crossbar architecture or SMP architecture. However, the interconnection network in case of dancehall architecture has large access latency and caching is a problem for coherence. Whereas in the fourth architecture, that is the distributed memory architecture shown over here, it has large-scale multiprocessor architecture where memory is distributed with non-uniform access time. Now, this is why this architecture is also referred to as non-uniform memory access or NUMA architecture. The Cray T3E is a typical example of NUMA architecture. As shown over here, it contains 1024 processors with 480 megabits per second links. Here, the non-local references are accessed using communication requests generated automatically by the memory controller in the external IOs. Here, as you can see, no hardware coherence mechanism is employed. Rather, directory-based cache coherence protocols are used. We will discuss the cache coherence protocols as well as the directory-based cache coherency in details next time. So far, we have been talking about the programming and communication models of shared memory address space architecture. Now, let us discuss the programming and communication models of message passing architecture. The programming model depicted over here illustrates that the whole computers, that is the CPU, memory, and I/O devices, they communicate as explicit I/O operations. Here, note that the message passing is essentially non-uniform memory access, but it is integrated at I/O devices versus memory systems. Here, the local memory is directly accessed, that is, it directly accesses the private address space. For example, the processor P directly accesses the local address X as shown over here, and the communication takes place via explicit message passing, that is, by using send, receive, where the send specifies local buffer and receiving process on remote computer, whereas the receive specifies sending process on remote computer and local buffer to place data. That is, in this example, the address Y on processor Q. Here, note that usually send includes a processing tag and receive has certain rules which it applies onto the tag. These rules are match one or match any other. The send and receive in this particular case is memory to memory copy, where each supplies local address and does pairwise synchronization. Here, the synchronization is achieved as follows. That is, receive waits for send when the send is complete. Then the buffer is made free and the request is accepted. So this gives us the programming model for message passing architecture. Now let us discuss the communication model for message passing architecture. The high-level block diagram for complete computer as a building block similar to the distributed shared address space is shown here to describe the communication abstraction. Here, the communication is integrated at I/O level and not into the memory system. Here you can see that it has networks for workstations or clusters, but tighter integration as compared to the shared memory system. It is easier to build than the scalable shared address space machines. The typical examples of message passing machines is IBM SP, which is shown over here. The IBM SP machine is made out of essentially complete RS6000 workstations. The network interface integrated into the I/O bus, and this architecture is one where the bandwidth is limited by the I/O bus. With this much discussion on to the programming model and communication model for message passing architecture, we close our discussion on to the parallel processing, where we have discussed the basics of parallel processing. We have explored how further improvements in computer performance can be accomplished by using parallel processing architecture. Today, we have described 4 categories of parallel architectures, that is SISD, SIMD, MISD, and MIMD architecture. Now, with this much discussion about the parallel processing, we stop here and Next time, inshallah, we will further take up the cache coherency problems and other related issues for parallel processing. Till then, Allah Hafiz. Thank you.